to take the difference between these two columns. I need to take the absolute value of those differences. I need to take the sum of those absolute values, and I need to divide them all by 2. And so now, when I call my total variation distance function on these two columns, it gives me a number 0.14. And so that's supposed to be a description of how different these two categorical distributions are. Do we agree? So it summarizes how different they are using just one number. You subtract the two values, so I'd have 0.11, 0.1, and so on and so forth. I would take the absolute values of those differences so that the positive ones don't cancel out the negative ones. I sum the absolute values, and then I divide by 2, and that's 0.14. And sure, okay, I could follow the formula, and it gives me 0.14, but what does it actually mean physically? Well, it turns out that there's this nice geometric interpretation. Okay, so here in red, I have my population distribution. So this is the ethnic distribution of everyone in Alameda County who is eligible to be on jury panels. And in blue, I have my observed sample of actual panelists. Okay, and I want to measure how different these two distributions are. That number 0.14, it turns out that it's the exact amount that all of the blue bars are longer than the red bars by. So if I take this distance here plus this distance here, I get 0.14. Now it's also equal to the amount that the red bars are longer than the blue bars by. So if I take this distance plus this distance, it's also 0.14. Okay, so that's one way to visually think about the total variation distance. Do we agree? Okay. Questions with the TVD so far and how it is defined? Yeah. It's so that we can have this nice interpretation. Right? If we didn't divide by 2, the TVD would be this length plus this length times 2. Right? It's just an arbitrary choice, but the choice of dividing by 2 makes the formula have this nice physical interpretation. Yeah?
So if you're counting the distance by which the bars are separated, like for instance in Latino,
yeah.
the blue bar is shorter than the red bar, but
yeah.
if you're trying to count up by like the blue bars, do you do like a negative value?
No, you would just look at the blue bars that are longer than red bars. Yeah. Good question. Okay, so it's really important to be able to understand how this calculation is done. And so to get you familiarized with it, here's a question that I'll give you a minute or so to tackle. Here are 2 more categorical distributions. I know they're categorical distributions because for each category I have some proportion, and the proportions all add up to 1 in both columns. Calculate the TVD between these 2 distributions, and enter in your answer at cc.dsc10.com. Go for it. cc.dsc10.com. Okay. Most common answer was B. Well, let's work through it. So remember, I need to take the absolute difference between the proportions in each category. So what's the absolute difference in the first two? 0.3. What about the second two? Third two? 0.2, and then the last two? Good. So this is the sum of the absolute differences. I need to take this sum and divide it by 2. That's the TVD, that's 0.3. Okay? Questions with how the TVD is computed? Yeah. It is necessary. For the TVD, it is necessary. Conceptually, you could come up with your own test statistic that doesn't divide by 2, and it would also see how different the two distributions are, but that wouldn't be the TVD. But the TVD, you will always divide by 2. Yeah? So your question is, why is this amount plus this amount the same as this amount plus this amount? Okay, take DSC 40A next quarter and they'll tell you. I'll tell you after class if you want, but it's just a mathematical fact. So I think there was another question. Yeah. Yeah, so it's an arbitrary choice. Like, we could make a valid test statistic without dividing by 2. The reason we divide by 2 is so that it has this nice interpretation, right? Like, the amount that the red bars are longer than the blue bars by, that's the TVD. The amount that the blue bars are longer than the red bars by, that's also the TVD. Not necessarily, no. Another way to think about the nice property we get because we divide by 2 is the fact that when you divide by 2, this distribution's distance from this one is 0.01. If you didn't divide by 2, it would be 0.02. Not that there's anything wrong with that, but 0.01 just feels more intuitive. Yeah, good questions. Okay, so the TVD is just a test statistic. Okay, and it's a test statistic, which means that we are going to compute it in each of our iterations of some sort of simulation. Right? So what we're going to do is simulate data under the assumption the null hypothesis is true. And here the null hypothesis is that jury panels are drawn at random from the eligible population. So what we're going to do is take our eligible population, draw a sample from it, and compute the TVD between our random samples ethnic distribution and the eligible population's ethnic distribution. That'll give us one test statistic. We draw another sample, we'll compute another TVD, that'll give us another test statistic. We do this over and over and over again. We'll get a distribution of test statistics, and then we can see where our observed test statistic lies in that distribution. So the only new part of this demonstration is the fact that our test statistic is new. Nothing else is new. Okay, so how do I actually simulate drawing from the eligible population? Well, you can run this. Oops. This is a categorical distribution. And can anyone remember the name of the function we talked about a few lessons ago that allows us to draw from a categorical distribution? Multinomial, right? np.random.multinomial. Good. What's our sample size here? Does anyone remember? 1,453, okay? And so what this does now is it samples 1,453 people from the distribution that's specified in this series. And so this is telling me that, recall, the first category was Asian. So in this sample of 1,453 people, 198 were Asian, and 267 were black, and so on and so forth. Now, distributions, for the TVD to work, our distributions need to be in terms of proportions, meaning that all of the values are between 0 and 1, and they add up to 1. So I just need to divide by the number of people I've selected. So now when I divide by 1453, this adds up to 1. So my sample distribution is then just this. Okay? So every time I run this cell, I'll get a new distribution. And you can see it changes every time. And each time, I'll compute the total variation distance between my eligible population and my sample's distribution. Not that it matters, but just to be consistent with the slide, do it in this order. Okay? So new sample, new TVD. New sample, new TVD. New sample, new TVD. You sort of see where we're going with this? right? I need to run this cell, or run these two cells many, many, many times, and that's what a for loop is for. Right, so now I'm going to draw 10,000 samples from the eligible population and compute 10,000 TVDs. And what I will always do after running such a simulation is I will look at the empirical distribution of my test statistic. Here's a question. Why are there no negative values of my test statistic? Yeah, because in the definition of the TVD, there's an absolute value, right? And it's measuring, the TVD is measuring how far apart two distributions are. And distances don't really make sense if they're negative. Right? The total variation distance, that has an absolute value, so it's going to be greater than 0. So what is this really telling us? This is telling us that if, under the assumption the null hypothesis is true, a randomly selected sample from the eligible population has a TVD of somewhere between, 0.005 and 0.03, typically. Right? If the null hypothesis were true, these would be the TVDs we'd expect to see in our observations. The TVD we actually saw was all the way over there, 0.14. Okay, so this is the distribution of the TVD under the assumption the null hypothesis is true. That's our observed TVD. So what's the conclusion we make here? Is our observed TVD consistent with the null hypothesis? No, right? If that black line was somewhere in the middle here or even here, we would say, okay, we don't really have evidence to say that the null hypothesis isn't true, so we will fail to reject it. But because that observed TVD is so far out of this distribution, it doesn't really seem plausible that it came from this distribution. Do we agree? Okay, so in this case, we would reject the null hypothesis. So it's pretty clear what the p-value will turn out to be here. What do you think the p-value will be? Right, it's 0, because the p-value, its formal definition, is the proportion of test statistics that were equal to your observed one or more extreme in the direction of the alternative hypothesis. And what's the direction of the alternative hypothesis here? To the left or to the right? To the right, right? Because distances are bigger when the distributions are different. And our alternative hypothesis is that the samples don't follow the same distribution as the population. So the alternative hypothesis is that our samples are different, and so that points to the direction of larger TVDs. So our p-value is the area to the right of this black line, but as we can see, there's nothing red to the right of this black line, so the p-value is 0. Do we agree with that reasoning? Okay. Now, if we wanted to actually calculate it, we could. TVDs greater than or equal to observed TVD. We can count how many of these are true and divide by 10,000, and we get 0. Okay. And you can see what this is telling us is that our observed sample looks much more different than a typical random sample from the population. Right? So here we have 3 distributions. In red, that's the population. That's what we sampled from. In blue, that's our actually observed panel. Like that's what we saw in real life. And in purple, we have a random sample, okay, drawn from the eligible population. And you can see the red and purple bars are almost the same length in all 5 categories. Do we agree? It's the observed panel that's different, right? Here the bar is longer, here it's shorter, here it's shorter, here it's longer. Right, so this is giving us more visual evidence that our sample doesn't seem like it was drawn at random from the eligible population. Sound good? Okay. So I guess we should also say for completeness that this is not telling us why the jury panels are not representative of the eligible population. It's just saying that they don't look like they're drawn at random from the eligible population. It says nothing about why. Right? We didn't do a randomized controlled trial or anything like that. Okay, what I just want to say is that the only thing that was new about this hypothesis test was the test statistic that we chose. It was the TVD, and we needed it because we were comparing categorical distributions repeatedly. None of our previous test statistics could do that. Okay, questions with our example so far? Sound good? Okay, So let's take stock of what we've done so far, right? Ever since we introduced the Robert Swain, Alabama example, all of the hypothesis tests, even before we called them that, they all were meant to answer a question of this form. I said, I have a population distribution, and I have one sample. Does this one sample look like it was drawn at random from the population? Every question we've answered so far has been of this form. For instance, we flipped a coin 400 times. Are these flips consistent with the coin being fair? The results of flipping this coin 400 times, that's our sample, and the population is a distribution that's 50% heads and 50% tails. So even though it's a little abstract to think of a fair coin as being a population, it is, right, because we can sample from it. Okay, so that question was of this form. So was, like I said, the Robert Swain jury panel example. The question we were answering was, did the jury panel, in the Swain case, in which there were only 8 black men, look like a random sample from the eligible population, in which there were 26 black men? That was the question we answered. That was of this form. And our favorite example, which might explain why more of you are in class now, is, were the midterm scores of our section, like did they look like a random sample of the entire course's midterm scores? Right? These questions, they were all of this one form. Do we agree? Everything we've done so far, there was a population, we knew what the population was, and we had one sample. The question was, did that one sample look like it was from the population? So we can do that now. But there's another class of questions that our current tools can't really answer. Here's the setup. Let's suppose we have 2 samples, but no information about any population distribution. All I have are 2 samples. And the question I want to ask is, do these samples look like they were drawn from the same population? Right? Our current tooling can't answer that because all of our hypothesis tests so far required us to sample from the population distribution that we already knew about. But if we don't know the population yet, well then our previous examples, the logic in our previous examples doesn't really follow here. Right? And so what's an example of this? Well, here's the one that we're going to look at today. I have 2 samples of weights of newborn babies. One sample contains the weights of babies whose mothers didn't smoke while pregnant. And one sample contains the weights of babies whose mothers did smoke while pregnant. Do these 2 samples of baby weights look like they're from the same population distribution? Well, it's kind of hard to answer that right now because I don't know what population distribution I'm talking about. I just have these 2 samples. The other example that we will look at likely on Friday is I have 2 samples of pressure drops of footballs provided by different teams. Do these pressure drops look like they're taken from the same population distribution? Again, I don't know what that population distribution is. I just want to know if these 2 samples are from the same one. So this flavor of question we can't yet answer, but we're going to learn how to answer it today. So these questions are answered through A/B testing, and permutation testing is one type of A/B testing, and it's the type that we will look at in this class. So let's look at a little bit of motivation. Let's think back to when number 44 was campaigning. And when Obama was campaigning, number 44, he was the 44th president. Okay, anyways. His campaign was testing different versions of a pop-up box on his website. And the goal of the pop-up box was to encourage people to donate to the campaign. Right? And so what they did was they gave each visitor to the site a slightly different combination of photo. Right? So here is just a picture of Obama, but you'll see there are other pictures, and buttons. So this one says sign up, but you can imagine the button could say other things like join us or donate now, stuff like that. So they gave different visitors different sites, and what they did was essentially they kept track of the number of people who clicked the box, or clicked the button, based off of every combination of photo and button. So they'll try one combination, record how many people donate. They'll record another combination, and record how many people donate, so on and so forth. They want to pick the best combination of photo and button. So here are the 4 button choices they used. Which one do you think would lead to the most signups? Yeah, I mean, I personally think it would be join us now, because it's like we're part of the movement, right? But I don't know, who's to say? This is why we collect data and survey thousands and thousands of people to see what they actually do. Okay? Well, here's the winning answer. The winning answer was learn more. Okay, and so this is the winning combination. And so also the picture is different than the one before. The picture before was, I think, him speaking at a rally or something like that, and this is one of his family. And this is the choice they ended up with, and it's estimated that by using this combination over whatever default they had before, the campaign brought in an extra $60 million of revenue that they used for ads and whatever else. Okay? And so what they did when testing different combinations of buttons and photos was A/B testing. They were collecting samples of the amount that people would donate and how frequently people would donate. And they were asking, were these samples of engagement drawn from the same population or were they not? Right? Like, was there a significant difference using this button over that button? So they were performing A/B tests. And as you'll see, A/B tests are one of the most commonly used tools from data science used in industry, especially in fields that don't use other parts of data science. Right? Like, everyone will use A/B testing. Not everyone will necessarily use bpd.read CSV. I don't know. That was a bad example. But A/B testing is very prevalent. That's my point. Okay? So as I alluded to earlier, the example we're going to look at involves the weights of babies born to mothers who didn't smoke and the weights of babies born to mothers who did smoke. Okay? Now that's annoying to say repeatedly, so I'm just going to say smoking babies and non-smoking babies. But it's clear that it's the mothers who are smoking and not the babies, hopefully. But we weren't there. We don't know. Okay? So we have access to data from an observational study. We have data on 1,174 babies. And the information we have on each baby is twofold. We have whether or not their mother smoked while pregnant, so that's maternal smoker. True is they smoked, false is they didn't. And we have their birth weight in ounces. Now, ounces are not that intuitive of a metric to me, but 100 ounces is equal to 6.25 pounds. Okay, so that'll help you calibrate what these values mean. Okay, and so, the question we're asking is, are these two distributions different? And so to be clear, the two distributions we're looking at are, in blue, the distribution of birth weights of smoking babies, and in red, the distribution of birth weights of non-smoking babies. Again, all we have access to are two samples. And these are the distributions of those two samples. What do you notice? There are only two distributions. This purple that you're seeing is a combination of red and blue. Yeah, good question. Yeah, the red is slightly to the right of the blue distribution. So which babies weighed more on average? The non-smoking babies or the smoking babies? The non-smoking babies, right? So it appears that in our sample, the non-smoking babies weighed more on average than the smoking babies. Okay? Do we agree with that observation? Non-smoking babies seemed like they were heavier. And so that's true in our sample, right? But notice we only have access to a data set with 1,174 rows. We, of course, don't have access to the population. And here the population would be every baby that has ever been born plus whether or not their mother smoked while pregnant, right? Like, we obviously don't have access to that, right? So the question we need to ask is, if we had access to that entire population distribution, would we see the same pattern, right? Is the pattern where non-smoking babies weigh more on average than smoking babies evident in the population, or is it just, present in our two samples due to random chance? Okay, and now, this set of questions should resemble earlier questions that we've addressed using hypothesis tests, right? The example we looked at last class was, did our section's midterm scores look like a random sample of the entire course's midterm scores, or were the differences due to random chance or not? We're asking the same question. Right? Is this pattern evident in the population, or are the differences significant? Okay? So do we see how this set of questions is the same as before? where we saw something in a sample, and we want to know whether this is true in a population or not. Okay, so let's start setting up a hypothesis test. Everything we're doing today is still under the framework of hypothesis testing, but it's a specific kind of hypothesis testing. So if it's a hypothesis test, we need null and alternative hypotheses. So here our null hypothesis is that the birth weights of smoking babies and non-smoking babies come from the same population distribution, and the observed differences we see in our two samples are just due to random chance. Like, it just happened to be the case that the smoking babies in our sample were lighter on average. Okay? The alternative hypothesis is no, these differences are not just due to random chance, but instead in the population, the smoking babies are actually lighter on average. Okay, so do we agree with these two hypotheses? Null hypothesis, they come from the same distribution. Alternative hypothesis, no, they don't come from the same distribution because the smoking babies are actually lighter. Or alternatively, the non-smoking babies are actually heavier on average. So do we agree with these two hypotheses? Okay. So when setting up a hypothesis test, after you establish your null and alternative hypotheses, we need to pick a test statistic. Right? And remember, our test statistic is a number we compute each time we run a simulation, and it should be such that large values of the test statistic point to one hypothesis and small point to the other. So we need to pick a test statistic here that will allow us to discern between these two hypotheses. Yeah? Not quite. What we're trying to do is, without having access to the population, we're trying to see if these two samples came from the same population. Yes. It'll become a little more clear in just a second. Okay, so here's our setup. Note we have two numerical distributions, right? We know they're numerical because we used histograms to draw them. And we need to pick a test statistic now. And so what I want you to do for maybe 30 seconds is talk to those around you and answer the question, why can't we use the TVD as a test statistic here? Why can't we use the TVD? Okay, discuss for 30 seconds. So can someone tell me, why can't we use the TVD here? Why can't we? It's not a trick question. We cannot. But why not? Close, close. Not quite, not quite. I think the first answer was a little closer, right? The TVD, it only does one thing. It compares how different two categorical distributions are. But the distributions here are not categorical, right? If they were categorical, we would visualize them with bar charts, right? And if they were categorical, we would have something like, in our previous example, the categories were like Asian, black, white, other, Latino, right? There are no such categories here. All we have are weights of smoking babies. Those are all numbers. We drew a histogram for them. And weights of non-smoking babies. Those were all numbers, and we drew a histogram for them as well. So there's no categorical distribution here, so there's no use for the TVD. Do we agree? Okay. TVD, only for categorical distributions. Okay, so what test statistic will we use? Well, here's one. We'll use the difference in group means, or just to keep it easy, the difference in means. So here's what I mean by that. We have two numerical samples, the non-smoking weights and the smoking weights. Those two numerical samples have averages, or means. So I can compute the average of the non-smoking weights, I can compute the average of the smoking weights, and I can just take the difference between them. And that'll be my test statistic. Okay, so here's a question. For our observed two samples, like the two samples whose histograms we drew. Should this test statistic be positive or negative? Do you think it'll be positive or negative? Yeah, positive. Why? Yeah, the non-smoking distribution, remember that was the red one, that was to the right of the smoking distribution. So we suspect that non-smoking babies weigh more on average than smoking babies. So this will be big number minus smaller number, and that'll be positive. And so along those lines, the bigger this test statistic is, the more we have evidence for the alternative hypothesis, right? Because remember, the alternative hypothesis was the non-smoking babies are heavier. So let's compute our observed test statistic. So remember, here's our data frame, babies. I can group by the maternal smoker column and use dot mean. And so now my observed statistic is this number minus this number. Just to keep it easy, I'll save this to a variable. And all I need to do now is use this variable, get the birth weight column, and dot loc false. So that'll be 123.09 or whatever. And subtract from that dot loc true. So this right here is my observed difference. But it's really my observed test statistic. Do we agree that this is the observed test statistic? It's the difference in average weights of non-smoking babies and smoking babies in the not in the population, in our two samples. Okay, you might ask, why did we do non-smoking minus smoking? Could we have done the other way, smoking minus non-smoking? Yeah, we could have. And this would just be negative 9.26 instead of positive 9.26. It's fine. You could do A minus B or B minus A, as long as you are consistent throughout your entire test which one you chose. We'll choose this one just so that our observed one turns out positive because it looks a little nicer, but we could have done the other way around. Sound good? Okay, so now we're almost ready to run our hypothesis test. We have our null and alternative hypotheses, we have our test statistic, but we now have to address that issue, right? The issue that we don't have the population distribution, so we can't draw samples from it. Okay? So here's what we need to do. We can construct a pseudo-population. Okay, we don't have access to the real population, so that makes this example different than our previous ones. But we can construct a pseudo-population by just combining both of our samples. Okay? We have the sample of non-smoking weights, the sample of smoking weights. Let's just lump them all together into one big group and pretend that that's our sample, or that's our population. And then, to create two new samples from that pseudo-population, we can just shuffle up that pseudo-population and split it up into two groups. And that will give us a new sample for non-smoking weights and a new sample for smoking weights. And the reason we can do any of this is because under the null hypothesis, essentially it's saying whether or not the mother smoked while pregnant has no effect or no bearing on the baby's birth weight. So it's essentially the null hypothesis is saying the maternal smoker column is irrelevant. So if you want to draw samples, just combine your two samples and ignore the maternal smoker column. That's what the null hypothesis is saying. Okay, so it's kind of weird to wrap your head around this. So we put together an animation. Okay, you can tell which emoji corresponds to which group. So here, for this example, we have 7 non-smoking weights, and the emoji that looks like it's vaping, those will be the 4 smoking weights. Okay? So these are our 2 separate samples, and those 2 samples have their own means, and our test statistic is the difference of those 2 means. Now, the numbers in this animation will only be relevant for the 11 data points we have here. Right? Our observed statistic was 9.26, not this, but you get the idea. Okay, so here's what I'm proposing. Let's just combine these 2 samples and call that our pseudo-population. And then, since we need to draw a new sample of non-smoking weights and a new sample of smoking weights, what I can do is just shuffle this pseudo-population and then split it up into a group of 7 and a group of 4. Okay, so I took this pseudo-population, split it up. I shuffled it, right, because these are not in the same order. And I said, okay, I'm going to take 7 of them and pretend that's my new non-smoking sample. Now that new non-smoking sample will have an average. And I'm going to take the other 4 and say that's my new smoking sample. And that new smoking sample will also have an average. Those 2 averages, in this case, are 130 and 128. They have a difference, it's 2. And so that will be my test statistic for my first iteration of my simulation. Okay, so now we found a way to simulate test statistics under the null hypothesis. And if I want another simulated test statistic, all I need to do is go back to this pseudo population, shuffle it up again, and then split it into a group of 7 and a group of 4. And so I've done that again. You'll see here's my sample of 7 new non-smoking weights and 4 new smoking weights. Right? Those samples have means, those means have a difference, and that'll be my test statistic. And I can do this again. Go back to the pseudo population, shuffle it up, split it up, get 2 new samples, and those samples have means, and they have a difference. Okay? The part that's likely confusing is why I see the smoking emoji over here sometimes and the non-smoking emoji over here sometimes, right? But if I always use the smoking emojis, the non-smoking emojis here and the smoking emojis here, well, I would always have the same 2 samples as I started with, right? Because when you change the order of 2 numbers, it doesn't change their sum or the average, right? The only reason I'm doing all of this is to generate new samples that look like they came from the population, so I can generate test statistics. And under the null hypothesis, whether the baby's mother smoked or not has no bearing on the weight, and so I can just ignore whether or not the baby's mother smoked or not for the purposes of generating these samples. Yeah? Not quite. That's not what we're doing here. We're actually combining the 2 samples, shuffling them up, and then re-separating them. No, what's different here is that we don't know what the actual population is. If you look back at every example we've done so far, we actually knew what the population was. Here we don't know and we still don't know, so this is just a trick to simulate new samples that look like they came from the population, when we actually don't know what the population is. We're just using the data we already have access to and shuffling it around to generate new samples that look like they came from the population. The reason we can do that is because the null hypothesis says that this emoji is irrelevant. That's what the null hypothesis is saying. So all you can do is just shuffle up the numbers, take 7 of them randomly, say that's one group, take the other 4, say that's another group, and take the averages from there. Yeah?
The proportion of the after segregation always follows our written note.
Yes, and that's important, right? There are 7 non-smoking emojis here, 7 non-smoking emojis here, and 7 non-smoking emojis here. That's intentional. Yeah, and that's important. And that's why I've intentionally said we take the pseudo population, shuffle it, and then split it, right? And when we do that, we keep the same number of emojis of each type in each row. Do we agree? Right, so here, 4 smoking emojis, also 4, also 4. Okay? So what questions do we have so far about all of this? Because if you're okay with this, then everything that follows is just how we implement this in code. Okay? This trick we're using is to generate new samples of non-smoking weights and smoking weights under the null hypothesis. Yeah?
Sorry, I'm still a little confused with why we're able to mix the smoking population with the non-smoking population.
It's because the null hypothesis says that whether or not the mother smoked while pregnant has no bearing on the weight. So under the null hypothesis, we can just ignore the emojis and pretend we have 11 numbers. Does that kind of make sense? Okay, it's a weird idea. This is one of the probably the most confusing ideas in the course. Okay, but we're using this trick to generate new data under the null hypothesis.
So can we generalize saying that if we're trying to play this trick here, no matter with what kind of circumstances, the null hypothesis have to assume that the 2 samples we're drawing from is, like the category of them is irrelevant to shuffle them actually.
Well, not irrelevant, but that they're the same, so it doesn't matter if they're there or not. Yeah. I mean, as you may have noticed, most of our null hypotheses are x and y are the same, or x and y are drawn from the same distribution, right? So let's think about mechanically how we would do this in code. A permutation is just a mathematical term. It's just what you get when you shuffle a sequence of values. So when you take a deck of cards and you shuffle it, what you get back is a permutation of those cards. Okay? And so what we were doing in the previous slide, by shuffling that pseudo-population, was essentially taking a permutation of the population. Right? You can see, if I go back here, each of these rows, 1, 2, and 3, were just shuffled versions of this row. We agree with that? I shuffled to get here, shuffled again to get here, and shuffled again to get here. And all I was accomplishing by doing this shuffling was picking 7 of my random data points, or 7 of my data points randomly, and putting them in one group. And the other 4, I put in the other group. Do we agree? So I take all of my 11 data points, mix them all up, so the two, smoking and non-smokings are mixed. I take 7 of them, say, okay, you're one group. Take the other 4, say you're the other group. Do we agree with that at a high level? Splitting 11 into 7 and 4. We'll keep going because we have a lot to cover, but we can talk about it after. So essentially what we were doing is we're taking our 11 data points and saying, okay, I'm going to pretend 7 of you are non-smokers. I don't care which 7. I don't care if you were originally smoking or not. I'm going to pretend 7 of you are non-smokers, and I'm going to pretend the other 4 are smokers. And functionally, the way I do this is by taking that column of trues and falses in my data frame and shuffling just that column, or taking a permutation of that column. Okay? And so that's what a permutation test does. It's a type of hypothesis test that tests whether 2 samples came from the same population. And the way that you conduct a permutation test is by shuffling the column that contains your group labels, so the column that contains your trues and falses. Each time you do that, in our case, you will randomly put 7 of your data points into the false group and 4 of your data points into the true group. Right? It's like coming up with that row of 7 of one emoji, or 7 emojis and then 4 emojis. Right? That's all you're doing when you're shuffling who's in true and who's in false. And when you come up with these 2 new samples, you can compute their difference in group means. And you can repeat this process over and over and over again to get that empirical distribution of the difference in group means. Okay, so, again, all that's really new here is how we are generating data under the null hypothesis. Once we know how to generate that data, the process is the same. You compute a test statistic, append it to an array, draw a distribution, look at a p-value. Okay, but the new point is how we are generating this data. Okay, and so let me show you how you do that. Let's just pretend we have this small data frame. What I want to do here, of course, these are not our trues and falses or weights, but what I want to do here is keep the y values the same, 1, 2, 3, 4, and 5, but I just want to shuffle the x column. Okay, so I want to keep the same y's in the same order, but I want to shuffle just the x's. Now, we've seen a method that can sample from a data frame without replacement. That was .sample. And if I give it 5 in this case, what that will do is it'll just essentially shuffle the rows in my data frame, but it'll do that together. Right? And what happened here is that even though the order of the rows are different, the x's all correspond to the same y's. Right? D is still 4, A is still 1, C is still 3. So that didn't change. So this doesn't really help us. Instead, what we need to use is this other function, np.random.permutation. And here's how that works. I'm going to get the x column here. That's a series. And I'm going to give it to np.random.permutation. Okay? And so now before it was A, B, C, D, E. Now it's A, E, D, C, B. Okay? And what I can do is assign this column back to the data frame. And now, if I look at the last 2 columns, I've accomplished my goal. I kept the y's in place, but I shuffled the x's. So now, y1 corresponds to C instead of A, and 2 corresponds to E, and 3 corresponds to B. Okay, so np.random.permutation is what we will use to shuffle 1 column of a data frame. Okay? And so we're just going to do the same thing here too, right? I'm going to start with my 2 columns, maternal smoker and birth weight. And what I've done is I've pulled out the maternal smoker column, and I've shuffled it. Okay? Now, this is kind of a bad example because the first three all look the same. So let's just shuffle it again. Okay, there you go. So now, notice the number of trues and falses in this column and this column, they're still the same. Right? The running example we've been using are 7 falses, 7 non-smokers, and 4 trues, 4 smokers. Those numbers, you just got to multiply them all by like 100 here. But the number of trues and falses hasn't changed. What has changed is which numbers correspond to which labels. Right? Before 120, right, the mother of this baby who weighed 120 ounces at birth truly didn't smoke. But for the purposes of generating new data, when I shuffled, we're going to put 120 in the true group. So that's the group with 4 data points in this example, or in our previous example. Okay? And so now, if I look at just these 2 columns, I have a new assignment of smoking and not to weights. So it's a way of generating new data under the null hypothesis. Okay? And just to show you really quickly, now when I drew these 2 new samples and I plot their distributions, what do you notice? Yeah, they look much more similar than our 2 original samples did. Right? And that kind of makes sense, right? Under the null hypothesis, if these 2 samples came from the same distribution, we'd expect them to look pretty similar. Not identical, but pretty similar. And so we can compute the difference in group means for this one sample. It's 0.777. We can put that in a function. And then we just repeat this process over and over again. I'll just show you that really quickly. Of course, we'll take this up again. I'll show you this really quickly. We do this over and over and over again, and you can see this distribution of difference in group means is centered around 0. Right? Because under the null hypothesis, the 2 groups come from the same distribution, so we would expect their means to be the same on average, and so the difference should be 0 on average. And then, again, once we come up with this distribution, the next step is to look at where our observed test statistic is and compare it to that distribution. And again, in this case, it seems like that observed difference we saw here, 9.26 ounces, is way larger than anything we ever saw under the null hypothesis. So here it doesn't seem like the weights of smoking and non-smoking babies come from the same distribution. Okay, we'll recap this example when we come back to class next time, but that's about it.